Okay. Hi, everyone. Thank you very much for coming. My name is Andrea Cioccarelli. I'm an Android and Kotlin developer. I'm a student. And today we're going to be taking a look at Android app security fundamentals. Now, I actually think we have time. I just wanted to start with a very quick poll. So if that's cool with you, just raise your hand after a question. For the streaming ones, I can see you. Now, how many people in this room have written code for an application which has been published on the Google Play Store? Okay, that's quite a lot of you. And subset of that, how many of those people have written code for a commercial application, so a software which has either in-app purchases or subscriptions or financial transactions, and which has been published to the Google Play Store? Okay, quite a lot of hands. And finally, how many of you know if in your application you have any kind of security mechanisms or Antipiracy detection to actually protect your transactions from Android attacks? Okay, a few hands. Very good. Now, today's talk is not going to attempt to teach you expert Android security or Android security at all. Well, yes, basic Android security. I'm myself not a security expert. What this talk is about, since the name I chose for the actual talk is actually a little bit vague, is the security of an Android application against some kind of attack. Now, there are many kinds and classes of attacks that you can conduct on an Android application. What is relevant for us developers is a local attack. So an attack that a user, so the person that you're supposedly trying to serve with your software and your application, does on his device, so locally, on the application that is installed on the device. And okay. This actually gets overlooked a lot during production software, and the main reason why Google has recently started publishing libraries such as Play Integrity is to raise awareness on this. And I actually want to go through the things that I have outlined here. Now, we're going to talk about content. I will divide the presentation in two parts. The first one is going to have context. So we're going to contextualize all the things that we have to talk about in the presentation. We will go through app anatomy and lifecycle so that we will get an idea about how your application works and on a security standpoint. Then we will go to protection use cases so that you can understand what part of your application and what kinds of application need which kind of protection. And we will talk about protection trade-offs, so things that you have to consider while adding security to your software, because as often you don't have anything for free, and if you add security mechanisms, you have to consider that you're going to have some cost at some point. And then we're going to switch to the security side of things, where we will be able to talk about attack vectors, so the things that a local attacker can do against your software. And once we've seen them and we know what we can expect, we can actually take a look at how to defend ourselves. And we have basically two ways. We have security countermeasures, which is what you do in-house. So you ship with your software security countermeasures that get to your application, it gets downloaded, and it has some kind of protection. Or you can rely on an external protection system that does the job for you. It is more articulated, it is more structured, but it has a higher efficiency. And then we will also take a look at passive security or structural security. The main point I want to make here is that for all your users, you have the application and you have many users, and most users, and that's actually something that I'm paraphrasing for Google itself on the Play Integrity page, most users are going to use your application as intended, as you built it, and exactly as you're planning, maybe without bugs. And some of them are not, and are going to use your application or try to mess with it and to tamper it. And all of this talk is introductory material and is going to try to teach you how to avoid that, basically. And I don't want to, the thing I want you to walk away with is not how to implement those things, because if you implement like yourself in-house security mechanisms, those things are very technical, are very like nightmare code, and you don't actually need to do that, because many people have implemented those things in either security libraries or external protection systems, and you have them at your disposal, and you can just use them. So the thing I want you to walk away with is the line of thought that you can use to assess an Android application and understand which kind of security mechanisms and which kind of security level it needs, whether you need at all to implement security features, or maybe it's fine without any kind of security check or any piracy countermeasure, and how you can point to the documentation. We will not see a lot of implementations because, again, it doesn't make a lot of sense to see code in this way, but I will leave you pointers and links to libraries, implementations, documentation, and external references for you to go and actually check out what we're going to do. And what I'm trying to make here is something that isn't maybe written down well in any article. It's scattered all over the web, and I'm trying to wrap it up in one session so that we can at least have some awareness about what you're doing. And okay, we're gonna start with app anatomy and endpoints. Okay, this is your application. And when I say this is your application, you're probably thinking this is your code, or this is your services, or this is whatever you're thinking right now. What I want to talk about is not your application as a developer, so as something that we've all been talking about in the last days. I want to talk about the application from the user side. So an application installed on some device. That's kind of a launcher icon, and something local on the device. Actually, app is name, but the more technical term that we should be using in this case is binary. Because you have your binary, you have your code, you compile your code, you have all the control of your code. You can build the APK file as you wish, then you ship it to Google Play, and when a user downloads your application, the APK binary file gets downloaded on his device, gets installed, and it's there. And the main thing that you have to be aware of, which is the issue actually, is that you do not have control over this binary. You have control over your code, your services, whatever you're building. You have control right up until the point that you ship it to Google Play, and then when it gets to the device, it gets to the user. And the user owns physically the device, and actually has control and can enforce that control to make whatever it wants with the device. Most of users, as we said, are benevolent users. They are well-intentioned and well-behaved, but they're not going to mess with your software, tamper with it. Some users are going to do that. You may call them cheaters if you're developing a game. You may call them pirates if you're developing a normal financial application. You may call them hackers if you're a news reporter. But what the point is that you have to deal with this situation. Almost every commercial application has these things, and we can actually talk about value, because value is the thing that you have to protect while considering this kind of scenario. The value is, well, actually I said value, but most of the times it's just monetary value, is what the revenue, what the money gets to your, hopefully, business. And so the binary itself of your software doesn't have any value, because the binary itself is shipped, is downloaded, but doesn't give you value. The thing that gives you value is the interaction from your binary to the external services that your binary actually connects to. The first one that comes to mind is Google Play, for example, when you make transactions or you make a purchase. And so you have a dependency between your binary that is on a device and the Play Store, and you have the purchase that goes through. You may have external services, which are like, for example, Firebase, or you may have AWS for storage, whatever. And you also have APIs. For example, if you have more complex scenario, you may have your self API on your backend. And those are all things that are factored in value, because they all cost money if you want, because they all change the value of money that you have. Google Play usually increases it because users buy software through it. Services, you usually have to pay for them, but you have still to consider them because they are value. And the thing is, your software is connected to those things, and it acts as a gateway between the user and your value points that we may just call endpoints. And the thing is, just as when you are developing a backend software, there is a saying that you say that you have to take all the input from the user and treat it as radioactive garbage. You have to treat all the user interaction that are coming through your binary as radioactive garbage, because you don't know whether they're coming from normal and well-intentioned users or they're coming from an attacker. And you can do that. We can actually see that we have a lot of things that can go wrong with your software, and can go that the user with the device can do to your software to make it misbehave or tamper with it. Those are how you should actually classify them. I will leave you the slides at the end. You can just do whatever. And those things are actually what can attack your software and what can get through your binary. And the point is, our binary is kind of stupid. It just interacts with the endpoints. So if you can modify, if you can patch it, if you can edit this data, if you can tamper with it, you can modify the transaction. And for example, you don't get the money, but the application gets pirated and it gets like the pro version anyways. Or you can interact with APIs, for example, premium APIs for your software, even if you don't have the premium version because the binary is compromised. And we run into all of this kind of thing. And the solution for this scenario is to add a security layer. A security layer is a layer which contains security countermeasures or relies on external protection systems to shield yourself against those kind of attacks and protect the interaction between your user, your hopefully well-intentioned users, and your services, cutting out all the users which you don't want to deal with because they are trying to use their device as leverage to get to your application binary. Yeah, I think that's about it for this slide. Yeah, okay. There is a difference between security layer and security environment. The security environment is the set of conditions that your application requires to run on some device. For example, you may have a banking software and you may say, I don't want my device to run on rooted devices. I don't want my software to run on rooted devices. I don't want my software to run on custom operating system, and we'll get to those in attack vectors. I don't want my software to run in an emulator. And those are your constraints, and those are what you actually expect your software to do or not to do. And then the job of the security layer is to enforce the conditions of the security environment and to report to the code point where you check for security conditions in your application, whether those conditions are actually met or they are not. Because if they are not met, maybe you want to not proceed with the transactions or deny API access to the user or deny service, because that's, again, up to you. Everyone here has different application, everyone here has different security environment, and therefore has a different security layer. And you have to, the point of this talk is getting you to actually determine which security environment and which security layer is appropriate for your application and get you to use the right tooling. Okay, we're gonna get to use cases so we can get a little bit more concrete and get to seeing some examples, because this has been rather abstract. I drew this scheme. It's very opinionated, but you can draw your one. The main point is that you have to do something that works for you or your company. And we have protection level. So no, we have value over here. No value means that your application doesn't have value. It's I put it because it's a table, but doesn't happen very often. Local value means that your software is the value of your software is just in the binary, so it doesn't have any interaction with any backend services or endpoints. It's just like a very good application, like a music player offline or whatever. And aggregated value means that the value of your software is not only in the binary, but is in the binary and in the transactions and interactions that the binary actually goes on to do with the server. And so the value is distributed between the backend and the frontend if you want. And on the columns, we have a free, paid, or financial. Free means software is free, doesn't free of charge. Paid means that you have to pay either to download it or you have in-app transactions to get money. And financial means that it actually deals with money. So it's like a banking software or something that maybe it doesn't cost you money directly, but it deals with your money, which is a harder use case to go through. And we may actually see that if you don't have any value or local value and your application is free, you don't actually need a lot of protection, where low is just not a lot of protection. This is an important point because you don't have to just put protection everywhere in your application just blindly. You have to understand where you have to put protection. If you have a paid application, even if you don't have value, if you have local value, you may want to put some stronger security mechanisms because you're still paying and you need to check for your licenses and you need to protect the software that you're trying to do. And if you have aggregated value, you get to you may want to have higher protection standards because you have not only your paid software to protect, but you also have your backend services, which should be protected as well. And when you get to financials, the things start to get more convoluted because you have many more kinds of security layers and security protections because it is a completely different environment and it would need its own conference, but we're going to focus on free and paid columns, and that's what I wanted to know. And those are some use cases. I thought about a calculator, so just offline software. Calculator doesn't do anything, just normal calculator. This is actually a perfect scenario for zero protection. It doesn't need protection because it doesn't have value. It doesn't interact with backend services. It doesn't have any interaction with the Google Play. It's just an offline software, does your thing. It's beautiful. You wrote it. It's free. It doesn't need any protection layer. Any kind of protection that you put into it is going to limit some users, and you don't need to limit users on a calculator software. You may have, next thing I thought about is a chess analyzer. You just have a chess position and it gives you through an engine locally, and it gives you who is winning and who is not. And it's the same as before, but it's just paid. You pay through Google Play to download the software. And in this case, you may have zero or low protection because, again, you don't have any interaction with backend services. You don't have any strong thing to protect. You may want to check your license because if someone just distributes the APK file of your chess analyzer to someone else, then you can just use it. And if you don't have any kind of checks in place, you cannot detect whether the user is legitimate users who bought your software or is just a user who has actually not bought your software. And then I thought about a task manager, which is just a more convoluted example because you have service endpoints, because you have custom APIs to deal, for example, with your tasks or whatever your application may contain. You have free download, but you have the harder scenario because you have inside application code that interacts with the Google Play to get pro version, for example. This is a perfect scenario for medium protection because actually, again, you have server value that you want to protect, and you have in-app purchases, which are the main kind of attack vector that attackers actually are trying to accomplish by tampering with your application. So this is a scenario where you may want to have some more level of protection. And then we can get to the high end on streaming services, for example, where you have a much more convoluted API for example, music. You have to distribute cover art, MP3 plays, and whatever. And you have subscription services and you run ads. And in this case, you would need high protection. Again, you may want to need high protection. It all depends on your policy and your security environment. But in this case, it would make sense to have higher protection than a task manager or a chess analyzer because you have many more things that you have to care about, and you have many more things that could go wrong with a user interacting with your software in a undesignated way. And we're going to get to trade-offs because nothing is actually free in this case, I said. And you have such things as under protection, where you don't have enough protection in your software, and you're actually susceptible to some kind of attacks that you wouldn't be if you had put a little bit more checks in your software. And this is bad because you're susceptible to some kind of attacks that you wouldn't be normally. And there is also such thing as overprotection, because again, you don't have to ship a nuclear arsenal with your software every time you just build it. You have to understand the minimum amount of protection that makes your software work and ship nothing more. Because if you ship more, you're going to exclude some kind of users, which wouldn't need to be excluded if you had shipped a smaller kind of security package or security layer. And so the point is just ship your right amount of security protection and nothing more, nothing less. And you also have protection implication because, again, it's not free to implement kind of protection. It is performance costly because it can vary widely, but it can go from just checking a build string somewhere in the operating system to just scanning the application list and finding some kind of application that you're trying to look for piracy. Or it can go as far as interacting with a service that needs internet access and it needs CPU time to do those kind of things. So the more security you add to your software, the more performance you're going to impact. That's not a bad thing. I mean, you need security, but you don't need to overdo it because it is going to impact your performance. It is going to increase the infrastructure of your product because the more you add, the more dependency you have, or the more code you have to maintain and actually update and work through. And if you depend on external services, you have to deal with the dependency on external services. And that increases the level of complexity in the infrastructure of your software. And you may also have negative feedback because some users may actually kind of get mad that you're trying to protect your software and send you threatening emails or bad Play Store reviews. And so that's something that you have to take consideration of. Okay. Okay. Now we can start talking about the security-related stuff. We have attack vectors, and I actually divided the attacks in 3 categories because we could just list them on a bullet point, but it wouldn't be effective because they can be categorized, and I think you may remember them better if you learn in which category they apply and how they work. So on a system level, we have a scenario where the whole Android stack is compromised, and you have this is the worst case scenario if you want, because the entire operating system is in control of the user. It can do whatever it wants, and it has many more ways to interact negatively with your software. And so you have the attacks enabled by system, which is the outermost layer if you want. Then you get to the medium layer, which is Antipiracy, which just doesn't involve the entire operating system. It all involves the application stack, because Antipiracy means that there is pirate software installed on the device. And so it all involves the application layer, and you have some other application which may be trying to interfere or tamper with your software as it runs, or as it, for example, makes transactions with Google or any other value service that you have in your software. And then you have integrity, which is the trickiest because it boils down to the security and integrity of your application binary. So we're not on the application plane, we're just in our single APK file, and we're trying to determine if it is the original genuine file that Google shipped, that Google Play shipped when we downloaded the thing, or if it is just a modified, tampered pirate binary that someone has reverse engineered and recompiled or modified, and we have to detect this kind of thing. So this is the kind of structure that we have for attacks. And on system, we're gonna have gross oversimplification because all of the bullet points that we're going to see are very, let's say, technical, and we could go and stay here to talk a week about, not me because I'm not an expert, but we could stay here a week on every point, and we're just going to walk through the attack vectors. Routing, the main points are not themselves bad, because I'm not saying routing is bad or the custom operating system are bad. I'm just saying they enable things which in turn may be bad for your application. So you have to understand them. But you cannot directly detect, for example, data editing tools. So you detect the category they belong to as a catch-all. And for example, routing, which means you have administrative access to your device and you can do things that you wouldn't normally be able to do on a non-rooted device, enables a lot of things because you have full operative system control, and you have, for example, data editing capabilities. You can edit the application preferences, databases, files, binaries, whatever a target software may have. You have administrative code execution because you can execute which kind of code you want, and you have memory access and violation because you have operative system control, and you can actually edit and modify the memory of the program as it runs, and this may not be your ideal scenario for a software that you're trying to protect. And you have emulated execution, which is not bad in itself, but it opens doors for reverse engineering or debugging your software, which is something that you may not want to have done by someone to reverse engineer and understand how your code works on an emulator, and it is usually easier to understand to reverse engineer software on an emulator than on a real device. Custom OS is, let's say, it can have lower security standards than normal Android certified operative systems, and so you may want to know that your application is running on this kind of operative system. It can be not unstable, and it can be easier to root this kind of operative system instead of the normal one. And you also can have administrative tools, which is just tools that use the access that the user has on the device to perform a specific task. And you may want to watch out for those too. And on the Antipiracy layer, you have pirate software, which means that you can have pirate software installed on the device alongside your application. You may not want to run alongside the application because pirate software implies that there may be some kind of attack coming or that has gone under your application, and those applications still, even if they don't have administrative access, they can have a potential runtime interference with your software and make it run in a way that it wasn't protected. It wasn't adequately protected to be in. And you can have custom patches, which is just a way to say that a tool applies a patch to your software, and so it modifies your software, and it modifies a custom component of your software to make it do a thing that you didn't program it to do. And then you may have malicious proxies, which is just a way to say there are components that are used by pirate software to interact with your application itself. And those things are bad because those things are detectable, but they are like proxy servers for service redirection from your Android application. And you may have interception because you have some kind of software which tracks, for example, the network traffic or what goes on in your application, and you may not want to have that. And at the end, you have integrity. And I drew this because you don't know what happens in your application level, because when you have your software and your software is compromised, you do not know which part of your software is compromised. In all the code that you wrote, you may have some things, some mechanisms that you put in place, some protections that you have, and you don't know which kind of things have been modified by an attacker and which one have been. And so if you don't know that, it is rather hard to identify attack vectors, because an attacker which is attacking your software can change whatever it wants and can recompile it on the device. And so it is a bit convoluted to understand what goes on in integrity. We're going to get to that later. Okay, now we have the security countermeasures. So what we actually do, those were the attack vectors. Now we can actually try to defend ourselves against security attacks. And we can use the same scheme. So we use the same hierarchy and the same gross oversimplifications. And on the system level, we can have root detection, because if we have, again, if we determine that root access is bad for our software, we can say we don't want our software to run alongside a device which has root access. And you can detect root access in many ways, and those are some of the ways which you can detect root access. Those are emulator detections, and all those things are just ways that you can detect those conditions on your device. And they are actually very easy to detect from a library, for example. And very often, all of these things that we are seeing in the screen get wrapped in a library, and your application depends on that library, so you don't actually have to do those things yourself, but you actually need to include a library with your software and tell the library which kind of thing you would actually need to work with your application. Then you have Antipiracy checks, which are just those ones are they're not a lot, because you just have to scan the installed application list, so the software that the Android device has installed on it, and you match it against a local dataset on what software you don't want your software to run alongside. So, for example, you may have a list of pirate software that you don't want to run with, and you make a scan of your actual software that is installed on the devices. If you see that there is a match, this means that your software is running alongside a pirate software, and you may not want that. And on integrity, we have kind of the same thing, because you have to put in place, in this case, you have to put in place protections and hard coding things inside your software, so that when it gets modified by someone and reinstalled somewhere, you have like tripwires inside your software that can tell you when something has gone wrong. For example, there are like standard ways in which attackers use your device to attack your application. And if you know those standard ways, which you don't need to know, but library developers actually do, you can go through those things and identify detect when something specific has gone wrong on your application. And then if you detect a specific thing which has gone wrong, you can infer that some kind of attack has been going on with your application against some attack, some integrity attack. And okay, all of this was to say that the probability of success is not 100%, because all of the code that we are seeing is something that the developer or library developer, most likely, you get a library, you put it in your code, you tell it, I want to check against those things, and the library check against those things. The point is, if your software gets developed, it gets modified by someone, you actually cannot know which parts of your software is going to be developed. And so the problem is that you cannot ensure that you have 100% success rate, because the software, the code that checks the security of your software is inside your software. And if someone tries to tamper with it or modify it, it may as well modify the code which checks for the security status of the device. And so you have to be very careful about this thing, because you don't have to rely on those kind of protections, on in-house application protection, if you have a high security standard. If you have like a normal or medium security standard, so you don't have a very sensitive to security application, it may work something like that. Later, I will point you to libraries which do exactly what I've been talking about. But you have to realize that those things are not like 100% success rate. If you need high protection, a high degree of fidelity, you don't need to use exclusively those kind of things, because they can fail and they can actually get extracted from your application software, recompiled, and it works just as if you didn't put the protection mechanisms in place. And the other interesting thing that you can use are external protection systems, which is actually there were a few. I was gonna talk about safety net, which got deprecated after I wrote the script. So I'm going to talk about app integrity, which is the successor that Google Play released and is going to hopefully maintain. And those things are just external services that you have to put inside your application, like this. And they're not like normal interactions, and because they work with a backend. You have, for example, Play integrity works with interactions between a backend server and the Google Play server, and you can send the Google Play interface telling him, I want, for example, to initiate a value transaction, for example, if you want to start a transaction for the Google Play or a service, and it is going to have an external service, so your server and Google Play service communicate, and not directly, and this thing is not it cannot fail, because actually your binary doesn't have the code that checks for this thing. So even if your binary gets attacked by all the things that we can see on the left, your code is still safe, because the actual decisions and the actual code that makes the choice is on somewhere safe, hopefully, and somewhere where it is not going to be attacked. The main difference between in-house security countermeasures, so things that you can bundle with your software and ship to production, and external services, so you just depend on a service to secure your software, is that with normal in-house security, they can be stripped away. And with external protections, they are required to perform the operation that you want to perform. And so they have a higher degree of fidelity, but you have to use a custom private server, and you have to make, let's say, more effort to build those things. And so it is a trade-off. If you need high protection, you may want to have something external that fails considerably less often. And if you just need a basic level of protection and integrity, you may want to use only the security layer of your application. And you may want to mix both when you want to have high degree of fidelity and protection of your software. And okay, here it just drove green. This is an extract on the Google Play Play integrity, and it is just the code that you have to use on it's from their documentation. And this is what makes an integrity application work, because you have your application, Google Play, and your app server, and they communicate with each other. And so the control of the interaction is not only in your application hand, which is actually where your attacker may want to use its control. It is in Google Play and your app server control. And so you have this distributed interaction where you're not the only one on this transaction, and so you can have more security. And okay, there is also another thing called passive security. We've been talking about dynamic security, if you want, and passive or structural security is a different kind of security. Structural means your application is made from the ground up to be secure. For example, you use encryption in shared preferences or inside software. You use dynamic code loading, or you use code obfuscation when you ship to production. And all those things, they're not like, they don't protect against a specific kind of attack, but they increase the security and the robustness of your software overall. While in dynamic security, which is what we've been talking about, you actually try to understand when your software is being attacked or is in a situation where you don't want it to operate in. And in this case, you cannot defend yourself. Defense is not an appropriate word. You just stop working and you stop the interactions that you deem valuable for you and your software. And ideally, you would have both of those things. Structural security, for example, if you encrypt your internal storage, your internal shared preferences, they shouldn't be read by anyone because they're in private memory. But it makes sense to encrypt them because if you run, for example, on a rooted device or on a device which has administrative access to all its file system files, this device may actually want to go on the shared preferences and see which kind of preferences you have enabled or not. And if you use encryption in this kind of thing, you make that thing much more difficult because it's encrypted, and you would need to decompile the application, get the key, understand which algorithm goes on in encrypting strings. If you just use plain security, so you don't have structural security, and you use your plain software, you have all the preferences in plain text. And if you run on a device which is compromised, someone may want to read them and actually modify them. For example, a lot of software uses just, for example, if you have a pro version of the app, they store the key, the pro version boolean, like is application pro user. When they make the transaction, they store it in the shared preferences. And so if you have root access on the device, you can just go there and modify the value. And the application reads the value and says, okay, I'm the pro user, even if I didn't make the transaction to Google Play. And that is not a good thing that happens, but it is a bad practice. And you can prevent it both with dynamic security because you can interact with and understand when your software integrity has been compromised, and with structural security because you don't directly defend against this attack, but if it happens, you're not involved. Okay, this was the presentation. I want to give you the libraries which are needed to make all of this thing work, because we've seen the implementation overview, and all of those libraries have a different, let's say, scope. And if you have, you should go check them out and understand which one you may want to have. They are very well documented, and some of them, and you have actually the capabilities that we've discussed on in-house security in these libraries. And for documentation, those are all the things that you should basically know about play integrity or safety net, and those are things that your software you will benefit from knowing, and they expand on what we've seen. And we see implementation details or tampering detection or security in Android. If you want to take photos or whatever, that's fine. So those are actually this is the end of the presentation. Yeah, I think I said everything I wanted to say. So thank you.